Okay, so let us come to the last portion of this performance and thrust, all this. So, we have looked at in details this different thrust coefficient and different efficiency level, and then we looked at turbojet turboprop and the other factors which can really impact the performance parameter. So, now just we would like to connect between the aircraft performance and the propulsion system. So, what we have looked at is the to some extent the performance in terms of the propulsion system, like how much fuel is going to be consumed, and due to the fuel consumption how far it can go, or with the endurance limit of the all this. So, that is where we go actually. So, we look at this last portion of the, again this is something you can think about performance, but this is making a connections between so the connection between aircraft performance and propulsion system. So, what we have looked at is this one, this quantity, but now this is the one which you want to look at now. So, that these two are kind of connected and one can see how these are kind of affecting. So, again we are assuming the level flight condition. So, if you recall what we talk about in the level flight, that if this is the aircraft, then in level flight this is how thrust is going to be working, this is the direction of the weight, this is lift and this is weight. So, obviously, when it is in the level flight condition, then the thrust force is balanced with the drag force and the lift is balanced with the weight of the body. So, any thrust which is available in excess, so that would be overcome the drag, can be applied to accelerate the vehicle. So, that is going to increase the kinetic energy, or so what you can see when this talking about this level flight. So, this the thrust which is, when we talk about that, this means the thrust which is available in excess of that required to overcome the drag. So, that this can be applied to accelerate the vehicle. So, that means increasing the kinetic energy or to cause the vehicle to climb up, that is increasing the potential energy. So, this is increasing the potential energy. Okay. So, to maximize the time allowed or the endurance, so to maximize endurance or time allowed for a fixed quantity of energy, let us say for fixed quantity of fuel, it is necessary to minimize the rate of energy uses. So, that means the power required which is drag into flight velocity, and so and also to maximize the range necessary to minimize L by D for a given weight, or for a given weight for a given weight to minimize drag. So, these are the two important criteria. That one hand we would like to maximize the endurance, so that and that is possible for a given amount of fuel, and the other hand we would like to maximize the range. So, that to maximize the range we have to minimize the L by D, or for a given weight to minimize drag. Now, we have vehicle drag. So, look at those components. So, there are two components of that. One is the parasitic drag, the other one is the induced drag. Okay. So, this parasitic drag is proportional to the flight velocity square, okay, or v square, and the part which is in this induced drag, or this is drag due to lift, that decreases in proportion to the inverse of the flight velocity. So, that means this also the flight. So, this is 1 by V. So, that means what happens if you look at this, let us say V, the flight speed, and this is the actual drag, or rather aircraft drag. So, with flight velocity parasitic drag will increase. So, it goes like that. So, this is parasitic one, which is proportional to V square, and induced drag would be 1 by V square. So, this will come down like this. So, this is induced drag, which is 1 by V square. So, in between, to compensate that, the total drag will go like this. So, that is the total drag. So, these are the different component of the drag. Now, what we have, C d is C naught d naught plus C L square by pi e A r, where L is half rho V square S C L, d is half rho V square S C d, is the wing efficiency factor, S is the area, and then rho density, C L and C d is the drag and this coefficient. So, what we can write then, that drag is half rho V square S C d naught plus L square by half rho V square S 1 by pi e A r. So, one thing to just to mention, A r is the aspect ratio. Okay. So, now what we get is that now we can write half rho V square is C d 0, then we get plus W square by half rho V square S 1 by pi E A R. So, since at level flight L and W they are same. Now, to the minimum drag condition is our interest. So, we have to minimize drag. So, for a given weight it can occurs at the condition of the maximum. So, this occurs at the condition of maximum lift to drag ratio. So, D is L d by L, which is d by L W C d by C L. Okay. Now, we can find out maximum lift to drag ratio by setting d C L C d naught plus C L square by pi E A R by C L to be 0. So, this is to for maximum, and what we can find that from here C L minimum drag is pi E A R C d naught, and C d minimum drag is 2 C d naught. So, what it gives us C L by C d max is half root pi E A R by C d naught, and we get the flight speed for minimum drag condition is root over W by half rho S C L mean drag, which is essentially 4 W by A square 1 by rho square C d naught pi E A R, that is 1 by 4. So, that is what you get. That is the for the minimum drag condition what could be the flight velocity and the things like that. Now, we can find out how much power would be required. So, now we can look at the propulsion system requirement. So, to maintain the steady level flight. So, this is from propulsion system requirement. What we get T required would be drag and power required would be T required into velocity, which is d into V. So, what we have power required would be half rho V square S C d naught plus W square by half rho V s 1 by pi E aspect ratio. So, again if you look at the sort of an this is flight speed of V and this is power required P required. So, this changes with and this goes like so. This curve is V sort of cube, this is 1 by V. So, my power required would lie like this. So, this is my P required, the actual. So, this is a typical power required curve for of an aircraft, and that is how. Now, the velocity for minimum power is obtained So, the velocity for minimum power is obtained by taking the derivative of the equation for pre-required with respect to V and setting it to equal to 0. So, when you take that, that means this means, so we will take dV by P required to be 0 and to find out that velocity which will. So, one can do the maths here, we are not going into that calculation because it would be quite straightforward. So, this is P required condition would be 4 by 3 W by S 1 by rho square C D naught 1 by pi E A R, that is 1 by 4. So, as we will see in the quickly that maximum endurance occurs when the minimum power is used to maintain the steady level flight. So, that means the maximum endurance that will be obtained when minimum power is used to maintain the level flight. Okay. And the maximum range, that is the distance travelled. So, maximum range will be obtained when the aircraft is flown at the most aerodynamically efficient condition. Okay. So, that is maximum CL by CD. So, now we find out that aircraft endurance, where now for a given amount of fuel, for a given fuel, what we the maximum endurance or the time is obtained for the flight condition corresponding to the minimum rate of energy or power required at the minimum power required. So, we can find out the aerodynamic configuration which provides the minimum energy expenditure. So, to do that we will again come back to this and this is what we can write due to level flight, and power is W C D by C L V. So, where V is root over W by half rho S C L. So, that gives us power would be W cube by half rho S into C D by C L to the power 3 by 2. Okay. So, here this goes 3 by 2, half rho C L half and C D by C L 3 by 2. So, the minimum power required. So, minimum power required or maximum endurance occurs when CL by 2 by CD is a maximum. So, that means this quantity, the inverse quantity is maximum. So, with we can do some little bit of algebra here and arrive at an expression for the maximum endurance. So, for max endurance we can set like ddCL of CD naught CL square by pi EAR CL by 3 by 2 which is 0. And what we will find from here, so you can do this much. So, CL for minimum power which is root over 3 pi EAR CD naught, and CD for minimum power would be 4 CD naught, and CL by CD for mean power would be root over 3 pi EAR by 16 CD naught, and at the same time V for minimum power would be like square root of W by half rho S CL minimum power, and if we put back the CL minimum power, this will get us 4 by 3 W by S square 1 by rho square 1 by CD naught 1 by pi E AR whole to the power 1 by 4. So, we get the minimum velocity and all this. So, the minimum power or the maximum endurance condition occurs at a speed which is roughly this roughly 3 to the power 1 by 4 76% of the minimum drag or maximum range condition, and the corresponding lift to drag ratio would be roughly show the 86% or something like that. So, if we look at that curve like what we have again, flight velocity p, this is so this will go like that. So, power required and so this is power required minimum CL by CD max, and this is the slope of P required by V, which is V by D. So, this is a relationship between maximum endurance and maximum range. So, this is relationship between maximum endurance and max lift. So, continuing, what we get that D minimum power is W 16 by 3 pi E A R, which is root. So, this can be substituted into d W by d T, which is m dot F into G, that is minus T m dot F G by T, that is minus T by specific impulse, which is minus D by ISP. So, is such that for maximum endurance what we get dW by dt is minus W by ISP 16 by 3 CD naught by pi E AR to the power half. So, now one can integrate this one to get the assuming the, so assuming ISP to be constant. So, what we get T max is ISP CD naught by pi E AR, which is minus half ln W initial by W final. So, that is what we get. Now, there is one more condition that we will take, the climbing flight. So, climbing flight condition. So, here we can say that the, if aircraft is like this, the free body diagram, let us say this is theta, or let us put like that, let us say this is theta, this is thrust, and this goes the height. So, this is L, this is drag, and this is weight. So, any excess in power beyond that is required to overcome the drag will cause the vehicle increase its kinetic or potential energy. So, we consider this by the by this case by resolving the forces into different direction of the flight and equating with the acceleration. So, this essentially the force balance of aircraft in climbing flight. So, what we get L minus W cos theta is W by G V d theta by dt, where V d theta by dt is the acceleration normal to flight path, and T minus d minus W sin theta, this would be W by G dV by dt, where dV by dt is the acceleration tangent to flight path. So, the change in height of the vehicle or the rate of climb, which is R by C. So, that is we can write that this is the change in height. So, this would be V sin theta V minus T by d W minus V by G dV by dt. So, we can write this in a form T v minus dV equals to W dH by dt plus ddt of half W by G V square. So, which is means P power available minus power required is W dH by dt plus dt by half V square. See, in other words, one can say that excess power should be change in potential energy plus change in kinetic energy. So, now for steady climbing flight, what we see that this R by C would be V T by dW, which is P avail minus P required by W, and the time to climb would be T would be H1 H2 by dH R by C, where P avail is eta propeller efficiency into P shaft. For example, P required is D into V. So, the power available is a function of propulsion system. So, it means the P avail is a function of propulsion system, flight velocity, altitude. So, altitude, etc. Typically, it takes a form such that this could be like, which is power, this is flight speed V. So, this goes like this comes like this. So, this is probably the power required curve, this is P available curve, and this is the shortest time to climb is where P avail minus P required is maximum. So, this is a typical behavior of power available as a function of flight speed. So, that means the shortest time to climb, it will occur at flight velocity, where, so this would be the corresponding flight velocity for T shortest. So, that means at that particular velocity your P available minus P required, this difference is also maximum, and that would take the time to climb flight. So, that is pretty much gives you an idea about so first we looked at the all this endurance, range and all this in terms of the propulsion system, where the fuel is consumed and all this, and this portion of the discussion, at least the today's discussion, would give you a fair amount of idea how the aircraft endurance and the range, they are connected with the propulsion system, and that pretty much that is what we would like to discuss on this performance thrust, and we will continue the discussion on the other topics in the next lecture.